So hello everyone and welcome to the second webinar of the Preparing for the PAT course 2023. So my name is Kat, my pronouns are she and her, and I am the Access Officer for the Department of Physics. So I run most of our programs for secondary school students, including all the stuff to support people interested in applying in physics. So this session is being recorded and will be made available to you tomorrow. A quick reminder of the housekeeping rules for those of you joining us on Zoom. You will be able to use the Q&A for any questions that you would like to be addressed. I'll let you know when this is switched on and ready to go. You will also be able to access the chat to share your thoughts, but keep it polite, keep it kind. Do not share any personal details or information, and don't use it for questions that you want us to answer. Keep those for the Q&A. If at any point you're feeling unsafe or concerned about anyone, you can contact our safeguarding lead, Sean, or you can message the host and panelists. But now that we are done with the housekeeping, let's get started. So last week we jumped straight in with some problems, but I wanted to pause this week and make sure that everyone is really happy with the course, because we've had lots of new joiners this week who've missed the introductory emails. And I'm going to take a few minutes just to talk about what our course looks like, a little bit about the PAT test, and then at the end of our webinar today, I'll take some time to run some Q&A sessions. So first things first, the PAT is the physics admissions test at Oxford University, and it must be sat by all candidates for physics, physics and philosophy, engineering and materials science. Your result on the PAT forms part of the information which admissions tutors use to decide who is shortlisted for the interviews which are held in December. To sit the PAT test, your school must register as a test centre and you must be registered as a candidate. Okay. This year, the PAT will be in a hybrid format with questions on screen and a paper answer booklet that will be scanned and returned to us for marking by your teachers or the exam invigilators. And the online test will include a built-in on-screen calculator. This webinar is part of the PAT preparation course, which we run on behalf of all the subjects who we just mentioned who require the PAT. The Preparing the PAT course is a set of 8 webinars, along with some problem sets in between and some summer assignments that we hope will provide you with all the information you need to take the PAT, to help you prepare for the PAT and be confident going into interviews if you are shortlisted. This timetable is at the bottom of every PAT email, and it's highlighted where we are in it so that you can follow our progress. In each session, I will fill you in on any updates or news as we get closer to key dates. This is our second webinar. You can see us highlighted in yellow. Last week, we had a session led by Rachel, a teacher who works closely with us, and you had a whistle-stop general problem-solving session, which included dimensional analysis, lots of hints and tips about diagrams and notation. If you hadn't had the chance to watch that yet, don't worry, it's available online, along with the questions that Rachel used and a document that links it to our PAT materials page, which looks like this. So the introduction to the problem solving, which you can see at the top in pink, has some of those general hints and tips, but it gives you a bit more detail than Rachel was able to go into in just one session. And then underneath there are all the links related to the first webinar. So there are the problems which Rachel was using, the recording of the session, and the problems which we asked you to take a look at before today, if you had time. The link to this page is in the emails that come around, so you don't need to hunt for it just now. And this page will be updated after every session and clearly labelled so that you can find everything. We've got our introduction, then our webinar. And then what I'm going to finish with before I introduce our undergraduates for today is just some key information, and I will do this every week. So this is the website where you can find all of the information that you need. I'll share this link in tomorrow morning's email, so you don't need to worry about it. But this is the most up-to-date page. It's the one to check first for any information that you need, and it's got an FAQ page, which is really helpful. And in fact, just today, it was updated to announce that Your school is now able to register as a test centre, and the website Your School Needs This is linked here. Now, please don't panic. This sounds like a really big deal that you need to sort out. You do not. So trust us, behind the scenes, your teachers are used to registering their school. They do it for all of the big exams and for any admissions test. Okay? Your school will get all of the details for this. This is not for you to worry about. Feel free to mention it to your teachers, particularly if they're new to preparing for the PAT. But you do not need to worry about this too much. Your teachers can contact us if they have any questions, and we'll be keeping an eye on that. A quick note, if anyone is applying who is not currently at school, so if, for example, you're in the process of taking a gap year, you can apply to sit the PAT at a school or venue that is a registered test centre, but you won't be able to do that until candidate registrations open on the 1st of September. So that's really your next key date. The test format, which I mentioned earlier, the hybrid format where we've got questions on screen and a paper answer booklet, is a new one. It's not a big change though. The questions will be really similar. The syllabus is unchanged. Even though it's not a big change though, we know people get nervous about change. So we don't want anyone feeling anxious. You will be able to access a trial version of the test screen so that you can see what it looks like in advance. It's not quite ready yet. As soon as it is, I will update you and show you the new format as part of this 5-minute introduction to each PAT webinar. But that is my quick passive introduction update. I hope it was helpful. I will take questions at the end, but for now, I'm going to stop screen sharing and introduce our two lovely undergraduates and recent graduates. They're going to be taking you through the problems which were set last Wednesday. If you didn't get a chance to look at those problems, I'll pop the link to them into the chat right now. So I'm going to stop sharing my screen. Let's get Nina and Anna onto screen and we can give them a wave. I can see Nina and Anna. Hello, guys. How are you today?
Good, thank you. I think Nina's going first.
Well, I am going to switch my screen off now. I'm going to hand over to Anna and Nina. I'm going to switch on the Q&A so that if there are any questions that people want to ask you, they can pop those in, and I'll pop the link in the chat as well. Thank you.
Nice, thank you. Right, hi everyone. My name is Nina. I just finished my undergrad at Oxford. I was at UNIF and I did physics. And from next year, I'm studying in Oxford for a PhD in physics. So I'll go through the first 3 problems you had. Let me share my screen. And I'll be keeping an eye on the chat and Q&A from time to time just to see if people have questions. So first problem concerns a ball of given mass which bounces on a hard surface. It says that every time it hits the floor, it loses a quarter of its kinetic energy, and if the ball is released from a certain height, it asks after how many bounces it will bounce no higher than a given height. So we can already see that this problem will concern kinetic, maybe potential energy because we have a height, so conservation of those two. We know the total energy is conserved, but then we see that some of its kinetic energy is lost. So let's see how we would set up such a problem. First thing I usually do, and I would recommend doing, is writing down all of the things we know and also a simple schematic of the problem. So yeah, as we saw, a ball is released from a given height. So I'm gonna, I'm gonna call this height h, and then it starts bouncing. And because it loses kinetic energy, and they tell me, like, they're asking after how many bounces it will reach a certain height. So after every bounce, it reaches a lower and lower height. So I'm gonna call the height we're looking for small h. So we know that the ball has a mass of 0.1 kilograms. Tell me if what I'm writing is clear and you can see everything. Nothing in the chat. Yeah, okay. So we have the mass of the ball. We have the initial height of 1 meter. And they ask after how many bounces would a ball bounce no higher than 0.25 meters. So we want our small h to be no bigger, so smaller or equal to 0.25 meters. So yeah, again, I like writing everything out. Also, if it's not in SI units, convert it to SI units just to not think about it afterwards, not make silly mistakes. And the other crucial information we have is it says after every time it hits the floor, it loses a quarter of its kinetic energy. So let's think about what's happening. We know that initially, when it's up here, it's just being released from rest. So its total energy, E. Okay, I haven't thought out my space, but let's write here. Its total energy would be the potential energy it has initially. So let's call it E0. And this would just be the formula we all know, mg, which is Earth's acceleration going downwards, its initial height. So this is all of the energy the ball has to begin with. It starts falling, and when it hits the ground, they say it loses a quarter of its kinetic energy. But when we think about it, at the ground, we can set up our coordinate system that the ground is our 0 level. So at the ground, it has 0 potential energy. So this full energy, which was initially the potential energy, is now fully kinetic energy. So let's call this kinetic energy 0. And now this, yeah, we don't really need an expression for kinetic energy because no one is mentioning speeds. We don't really have anything that shows that we would want that, right? Point is, at this point here, it says that it loses a quarter of its kinetic energy. So it reaches the ground with this energy, and then E1 now, so these were E0, becomes 3/4 of E0. Again, what I'm trying to convey is that all of its energy is kinetic energy here. Therefore, when it loses a quarter of its kinetic energy, this means it loses a quarter of its full energy. And you can already see that once it flies up here, its overall energy doesn't change because we don't have any forces acting on it. At this point, it's the same as in this point. It comes to rest at the top before it starts falling down again. So here it will only have potential energy 1, and this potential energy 1 will be our 3/4 of the initial energy. So overall, what this process looks like is that it comes with some energy, loses a quarter of it, reaches a new height with 3/4 of that energy, comes down, loses 1/4 of this new energy, and so on and so forth. So we can see that after n jumps, after n jumps, the energy which the ball will have will be 3/4 of 3/4 of 3/4 of 3/4 n times of our initial energy. And I think this is the important setup of the problem, right? Yes. So we have an expression for this energy, and we're looking for the height. So we want to connect this h, the big H, which we know, to the small h. So the initial energy, we agreed that we can also write as mgh. This would be equal to 3/4 to the power n. This is an n, not an h. Just make it clear in case somebody is writing along. Oh, I'm sorry. So what I wanted to say is that the energy which we get at some point, which is mg small h, which we have reached after n bounces, is this fraction of the initial energy, which is mg big H. Let me just look at the chat because something's happening. Geometric series. I got 4. Okay, people are working through it, which is good. Okay, so first thing to notice is those two things cancel out, which is kind of interesting because it turns out that it doesn't matter what the mass of the ball is. So if you just throw down something huge or a tiny ping pong ball, it'll, if it loses the same amount of energy at the bottom, it'll make the same number of jumps before it starts jumping to below 0.25 meters. You don't have to point out clever things on the exam. It's just something to point out now, just because it gives you some sort of physics intuition. Okay, so what we know for H is this condition here. This is what we're looking for, right? And the question is how many jumps? So we're after n. So H, which is 3/4 to the power n times H, which now I'm going to substitute as 1 meter just to make, actually, yeah, let's keep that, times 1 meter is smaller or equal to 0.25 meters. And I'm substituting this just to point out that when we divide by 1 meter, the big H doesn't just disappear. We're in fact getting rid of the unit of this equation. So this is what we end up with as an equation. Okay, the chat is going wild. Okay, I won't be able to follow the chat because there's a lot of things happening. So if you have a question on the problem, put it in the Q&A. Also, if something is wrong with my screen or audio or something, also put it in the Q&A because I don't see what's happening in the chat.
Nina, I'll just jump in there. I think people on the chat are just talking to each other, so don't you worry. Any questions,
Okay.
I'll redirect over to the Q&A.
Okay, thank you so much for this. Okay, so again, we're after this n, so the logical thing to do is take a log of both sides. Here, the important thing is that we're taking a log of a fraction, so something smaller than 1. And if you remember, the log function, so if this is our variable x, and this is a natural log of x, it has this shape. So it crosses the axis at 1. So what I'm trying to say is that a log of something smaller than 1 is a negative number, which means that this sign here should change because it's the equivalent of multiplying by -1. So if this is smaller than this, if we multiply it by -1, or if we take the log, this will all of a sudden be bigger than this. It's just because of the behavior of this function. So now our equation will take the form log of 3/4 to the power of n is bigger or equal to log of 1/4. And yeah, we know the property of logs that this power we can take outside of the log. So n times log 3/4 is bigger or equal to log of 1/4. And if you put in your calculator what log of 1/4, well, log of 3/4 is, and you divide, and those are positive numbers, so you don't have a problem with dividing, you would get that n is bigger or equal to 4.81. So if you get to this answer, you already have more or less done the problem. Maybe it's worth putting in some thought into what this means. So what they asked us is how many bounces the ball needs before it stops reaching anything above 25 meters. So basically after its fourth bounce, it'll still reach something above 0.25 meters, but then after its fifth bounce, it'll no longer reach it. Is what the translation of this thing here is. There's one thing in the Q&A. Does the inequality sign not switch around in the second last line? Second, I'm not sure when this question was posted. Is this the second to last line you mean? Let me switch to another color just to be able to. So if you mean this line, not really, because you just take the power, the power of the argument out, and this is just a property of logs. The sign changes when you take the log of both sides, just because of how the function behaves, basically. Ask again if I'm answering a bit delayed. But yeah, that's the main idea of the problem. Do you guys have any other questions you would like me to explain?
Thanks so much, Nina. We've not had anything else come through in Q&A yet, so I was monitoring the chat while you were doing that. And I think what was lovely is we had lots of people discussing other ways that they were doing it as well, which is great.
Perfect. Obviously, if you have questions on previous problems and you need time to type them out, just type them out calmly and we'll go back and answer.
Absolutely. So just for everyone's attention, I'm monitoring the chat. So if you type into the Q&A, if you need an actual question answered, and we'll come back to each question afterwards. So should we move on to the next problem and I'll keep monitoring the Q&A for you guys?
Yeah.
Awesome.
So, yeah, the second. Nope. Having trouble. Cool. Yeah, this was meant to be a 2. So, second problem concerns snowman made out of modeling clay. We know that this is made out of 2 spheres. We have their radii, but the modeling clay comes as a cylinder, and they're asking what length of the modeling clay is needed. So in those cases, I like drawing. I generally like drawing, and I think examiners like seeing drawings. So it's good practice. We can draw a snowman of spheres. So one sphere has a radius r, the other sphere has radius 2r, and then we know the clay comes as a cylinder. Oof, this is a very bad cylinder. But if you draw this on an exam, it's fine. They know it's a cylinder. So don't stress about it. So it has some length, which we're looking for. And we know its radius is r over 2. Cool. Yeah, so we know that we have the cylinder, we have to change it in a way to make 2 spheres. What is constant throughout this process is the volume. So what would be an intuitive thing to do is to equate the volume of the snowman to the volume of the cylinder it has to be made from. What I would do in an exam is write out volume of sphere equals 4/3 p radius of sphere to the third, and then volume of cylinder equals p r cylinder squared times length of cylinder. Just to put it out there that these are the formulas you're using. Those are some, radii which just hold the place and show what you're going to be using. Maybe write a couple of words equating the volumes column and then start writing your equations. But because it's a bit hard to write here, I'm just going to write equations. So basically, what we want is the volume of the 2 spheres. So that would be 3/4 pi, and then r squared of the 2 things. So one of the spheres has a radius r to the third, and then the other one has radius 2r to the third. And this should be equal to pi r squared, and the radius of the cylinder is half r times the length we are looking for. So at this stage, you have set your equation and you can stop thinking about the physics and just do the maths. So don't care about pi. You have that 4/3. So this would be 1 plus 8, 9, r to the third equals 1/4 r squared times L. So I won't write out everything, but you can see that in this equation you have numbers. You have r to the third, r to the second. So you will get an expression for L in terms of r. And this is fine because you're just given it as a parameter. You don't get a length for it, but it's given in the problem statement, so you can leave it in the answer without any problem. And it turns out that this is 48 times r is the answer. So this is pretty straightforward, but it's mainly to visualize what's happening, and also remember these are spheres and not circles. So remember that it's physics. Okay.
Lovely. Thanks so much, Nina. I think people seem to be a lot more confident with that one. We had quite a lot of people sharing their answer.
There are questions on the inequality sign change in the previous question. Should I go back?
Yes, that's going back to your previous one. Does that make sense to you, or do you want us to take a break and you can come back to it when you've got the solutions ready again?
Sorry?
Does that make sense? Do you want to discuss that now, or do you want us to come back to you in a couple of minutes?
I'm trying to figure out, so why doesn't the inequality sign change when you divide by a log which is negative? Okay, it makes sense that it should be like that. Okay, I think I'm gonna go through the next question and then come back to this just for time's sake.
Awesome, thanks so much, Nina. So anyone who had that problem, Nina's going to have a quick look through problem one again in just a sec.
I just had a thought, if it's helpful. I think perhaps Nina changed the way around of the inequality one step too soon. I think taking logs of both sides, you multiply both by negative, so it should say the same. But then the next time you then divided, which is, I think, what's confused everyone, because you then divided by 1. So then I think it should have changed. I could be wrong. Maybe it's better to go back.
Thanks,
I think I know what I did.
I'll tell you what, why don't we'll leave that problem just now. So everyone who's asking about inequalities, we'll take another look at it. Let's have a look at the third problem now, and then we'll come back to it, okay?
Okay, yeah, and I'll go through it
guys.
slowly and explain. Yes, thank you. Yeah, I think I got what I did. Okay, that's fine. So the third problem, yes, this is the springs and connecting them in different ways. So basically what you're given, if I can scroll down, is a formula for the period of a spring with, a spring pendulum. So you may have done that at school, you may have not, and there will be some problems where they're just like, here is a formula which describes this and that. Tell me how the formula will change if you change this parameter or that parameter. And this is just to see that you can take something they give you and work with it, which is basically what we do in tutorials, right? They give you some new information, you're expected to kind of work with it and be able to manipulate it. So it doesn't matter whether you have done that at school and know where it's coming from, you don't care where it's coming from. So in part A, they ask what the period of oscillations of the mass would be if the gravitational strength was changed from G, which is the usual, to 2G. This is a bit of a trick question because if you look at the formula, you don't have the acceleration. The period only depends on the mass of the pendulum, the weight on the spring and the coefficient of the spring. So yeah, no change here. If you went to space with that spring with the same weight, it would oscillate at the same frequency with the same period. And yeah, this is something kind of useful. This is how you can weigh things in space. So you can't really use the gravitational acceleration like on Earth to just put a thing on a scale. In space, if you want to weigh something, you measure its period and you know the coefficient of the spring, and so you know its mass. Part B, what would the period oscillation of the mass be if it were hung from the two springs connected end to end in series? So the situation now is that we have one spring, and then we have a second spring connected to it in series, and then we have our weight M. So let's say that their coefficients for now are K1 and K2. We know they're equal, but just to make it easy to explain where things are coming from. So how do we deal with this? We know that the connection between M and K is through the force, right? We know that if you extend a spring by amount delta X, you'll get a returning force, which is equal to the coefficient of that spring times the extension, right? I'm going to remove that just to not confuse notation, but we can use that. And also the idea is that when the mass is hanging on both of them in series, the force it exerts on them, it's the same force exerted on both springs. So it's pulling them together. So in this case, we can say that the force, which is just the weight of the mass, right, would be equal to, on one hand, some new coefficient. So the equivalent spring, think of connecting resistors in series or in parallel, you have an equivalent resistor. So in the same way, you can think of an equivalent spring with this coefficient K prime times the extension, which we get, but also, actually, maybe it'll be easier to write it like that. But also, on the other hand, we know that this extension is equal to x1 plus x2. And x1 and x2 can be written as the same force F, because we agreed it's the same on both, over K1, again from this formula, and this is F over K2. So you can see that we can combine all of this, and we can write that X from here, which is just our total force over our new coefficient, is equal to that same F over K1 plus F over K2, or this would be equal to 2F over K if we agree that K1 is equal to K2 is equal to just K, because we're told that the two springs are the same. Again, I'm just writing the coefficients to keep track of the idea. We don't care about the force, and therefore we can see that K prime equals K over 2. So this is the coefficient of the equivalent spring, and we have our formula here. So our new period would be 2 pi m over K prime, which is K over 2. All of this under square root, and we can see that T prime would be equal to square root of the original T. So we'll have a longer period. So this is how you combine springs, and yeah, we could say that springs in series combine the same way resistors in parallel do. This doesn't really make any like physical, well, I guess it makes a bit of physical sense, but it's a way to remember it if you don't want to derive it every time you're in an exam. But yeah, Let me just check the Q&A. I'm pretty sure this is a topic that I haven't learned at all at school, so I was wondering what area of physics this is so I can cover it. What area of physics is like mechanics, dynamics, oscillations? Do you know, Kat?
Yeah, I was just saying it's a bit. I'd expect to find it in classical mechanics personally. So what I'd say, Katie, is check out the PAT syllabus. So again, I'm going to share all of these links, and you'll be able to find it. And then A-level revision guides are usually a really good place to start. If you can find a nice general one that covers exam boards other than your own, you can usually find this. So I'll make a note to myself, and I'll share some good revision links for you guys in my email tomorrow morning. And I think, Nina, we've just got one about why K doesn't change as well.
Yeah, so in part A, why does K not change? Because using F equals ma, the acceleration is greater. Yeah, so you're saying F, which is everything for, let me just think about the difference. Yeah, so the F which changes is this F. So basically, you're pulling, in this case, the situation is you just have only one spring, right? So you're pulling with a different force because the acceleration is different. Then just the extension of your spring will be different because the coefficient of the spring, the coefficient of elasticity, is a property of the spring itself. So the material it's made of. If the spring is made of aluminium, its coefficient will be different than the coefficient of a rubber spring or a different metal. So in this second case, the coefficient of elasticity does not change. It's just of the spring itself. Like if you just separate those two, each of the case for each of the springs will be the same. We have an effective coefficient, which is different to the original coefficients just because of the fact we are combining a couple of springs together. Whereas in the first part, we're changing the acceleration. Yes, this means the force changes, but then you would just expand the spring more. The spring itself with its coefficient, which is a fundamental property to the material the spring is made of, won't change. So this is why. Hopefully this makes sense.
That was great. That was really helpful. Thank you, Nina. And while I've been manning the chat, it's great because there's no way that we can keep on top of every single exam board. So everyone's been sharing where it is in their particular exam board. So we've solved the mystery of where springs are covered, which is great.
Yeah. So does that mean that if G becomes 2G, the force would double, so the extension would double, so it cancels out? Yeah, in F equals K delta X. Yes, exactly what happens. So yeah. Have you learned more about springs in your degree? Have I learned more about springs in my degree? I've learned more about deformation of springs. So what happens if you pull a bit too much and it's like it no longer just bounces back, it starts behaving weirdly, and like the thermodynamics of this whole thing. But I think just for like simple harmonic motion, I can describe it with a differential equation, but that's it. I haven't really learned too much more. I can do a bit fancier maths.
Yeah, I was going to say very fancy maths. There's certainly a lot of simple harmonic motion maths from what I remember. Okay, Nina, I think that was a great first 3 questions. Thank you so much. We're going to push on.
Part.
Oh, have you got one more?
Part?
Oh,
yes, yeah. I'll try to go quickly through it.
We're ready to go. Carry on, Nina.
I'm taking my time explaining everything. Yeah, so second part, again, 2 springs, this time in parallel. Again, we're going to go with K1 and K2. This time, you're pulling on the thing with the same force, but it's divided equally between the 2 springs because they're kind of helping each other. If you hang a bag on hangers, you prefer to hang it on 2 hangers just to not pull the hanger out of the wall. So in this case, the total force would be F1 plus F2. So each of the forces applied to these, again, when the coefficients are the same, those forces will be the same. I'm just keeping the coefficients like these numbers, just for clarity. So if you substitute our effective coefficient K prime times the extension, it will be the same because the force is applied like in the middle. So they extend by the same amount. Would be K1 x1 plus K2 x2. As I just said, x1 would be equal to x2, and this would be equal to x, just everything gets extended by the same amount. So these can go. These two are the same. So our effective coefficient would be twice the coefficient of each of the springs. And if you just substitute it into the formula you're given, T prime would be equal to T over root 2. And again, if you want to remember it, springs add the opposite to resistors. So in series, they add the same way the resistors would add in parallel. But yeah, it's like 2 lines to derive it. So that would be easier. Cool. So these are the problems.
Lovely. I was impressed even before you did the final section, Nina. So thank you. I think what we should do now is, because I know you're going to return to question 1 for us. So why don't we hand over to Anna? We'll let Anna cover her problems, and that'll give you a chance to take a break, Nina, and then come back to us and talk to us about that inequality. Does that sound all right?
Thank you.
Great. Thank you so much, Nina.
Great. Well, hi everyone. I'm Anna.
Hi.
I also just finished a degree in physics at Oxford. I was at a different college to Nina, and I'm not quite sure what I'll do next year. But still very much enjoying physics now. And just on the topic of springs, I was thinking in 3rd and 4th year of our degree, we did a lot of modeling solids as like blobs connected by springs. So yeah, learn springs, they come up a lot.
I love it. And I think it's quite reasonable not to know what you want to do 3 days after you finish exams, Anna. I'm just going to point that out. But you're good to go.
Right, I'll share my screen.
Lovely. I'll do the same. I'll monitor the chat for you, keep that going, and pass anything over to the Q&A that you need.
Great. Can you see this just before you disappear?
I can.
Great. I don't think, I hope I can draw. At the moment it's not giving me the option to. I'll just plug my tablet back in. There's usually a little pen picture at the top, which I can't see at the moment. I don't know if you have any ideas, Kat.
No, I was just having a look. All of our settings are definitely on. So I've not stopped you being able to use that.
Okay, well, I'll just, I'll try and do it through Word instead. Sorry, let me just stop sharing, work out how to do it through Word, and then I'll share again.
We're all right, don't worry, we'll figure it out.
So, I go to File. I think I just have to change the way I'm viewing the document, which might give a little bit less space for everyone to see what I'm doing, but hopefully.
That's right, because we're on computers, people will be able to zoom in as well, so.
That's true. Right, let's try again. Right, so.
Yep, we can see your screen, I can see your pens.
Perfect. So yes, question 4. We have a ball thrown at an angle of 30 degrees up from the horizontal at a speed of 10 meters per second off the top of a cliff, which is 10 meters high above a flat beach. So like Nina kept saying, it's a really good idea to draw a picture. So if we draw our cliff, which is 10 meters high, and we have a flat beach. Sorry about my drawing. And we have a ball being thrown at an angle of 30 degrees above the horizontal. So we want to know how long does it take for the ball to hit the beach below. And we may assume that the acceleration due to gravity is 10 and the air resistance can be neglected. So hopefully you might spot that the only force acting on the ball once we've thrown it is gravity. So we can use our constant acceleration equations. So that's our SUVAT equations, which hopefully you will have met, but if not, I will explain. So in this question, what we need to do is identify, we'll do it vertically because we want to know how long it takes for the ball to hit the beach. So that's how long it travels downwards. So S is the displacement that it finishes with. So if we take positive as being upwards, then at the end when it hits the beach, the positive displacement would be -10. And then U is the initial velocity. So that would be, start with 10 meters per second. So the initial velocity only in the vertical direction, that would be 10 sine 30, which, using the fact that sine 30 is half, is 5. Then we have our final velocity, which we don't know. We have A, the acceleration, which we're told gravity is 10, but again, we're taking positive as upwards, so the acceleration is -10. And then the time, this is what we want to find out. So there are lots of different SUVAT equations, and we want the one that involves S, U, A, and T, but not V. So that one is S equals UT plus a half AT squared. So now we need to plug all these numbers in. So S, we have -10. U, we have 5. T, we don't know. And then A is -10, so half of that, we have -5t squared. So if I just scroll down. So now we want to rearrange this equation so we can solve it. So if we take this and this both to the left to join the -10, we will have 5t squared minus 5t minus 10 equals 0, as long as I haven't made a sign error, which I don't think I have. So then we want to divide everything by 5, because we can see that everything here is divisible by 5. So we've got t squared minus t minus 2 equals 0. And now we just need to factorize it. So I'm going to guess we have a t here and a t here. And we want -2, but minus t as well. So if we have -2 here and +1 here, then we'll have -2 plus 1t, so that's -1t. And then -2 times 1 is -2. So this means our solutions are t equals 2 seconds and t equals -1 seconds, but we can ignore this because that's not physical. That would be the ball going backwards into the cliff. So our answer is t is 2 seconds. We'll have a look at the Q&A. Sorry, I've gone too quickly. Oh no, there's a question for Nina about pursuing your PhD that maybe Nina can type. And does simple harmonic motion appear in quantum mechanics with wave functions, etc.? Sort of. Similar differential equations. You don't quite end up with a quantum mechanical spring, but you end up with, you have a simple harmonic oscillator, and with quantum mechanics, you use a quantum harmonic oscillator a lot, which is like the quantum mechanics version. Does the negative answer tell us the time for the ball to go up the cliff from the ground? The negative answer tells us, so I'll just draw this down here. So we have the cliff and we have the ball being thrown like this, and it travels like that. And we've just calculated the time for it to reach here. But if you imagine it going backwards in time, but kind of assuming that it wasn't thrown originally, that it just followed the trajectory that it's on now, because we kind of, once it's been thrown, we kind of assume it travels like that as though it wasn't thrown. Maybe this doesn't make sense, but if I draw it, so you can see that if you go backwards in time, ignoring the fact that it was thrown and it can't travel through the earth, it would then touch the beach at -1 second. So it really doesn't make any physical sense, but you just get two solutions because the equation is for this quadratic, which involves the cliff. Yeah,
I think your diagram shows that really nicely, Anna. Don't panic.
Right, I will stop showing question 4 and then start showing question 5 once I've rejigged that one in the same way. I set it all up so nicely. Right, there we go. Oh, you're muted, Kat. Or I've frozen. I didn't, if you're talking to me, Kat, I couldn't hear it. Because you're muted, but I will share question 5.
Perfect, thank you.
Right. So, draw. This one's a tricky one. Or I find it difficult at least. I walk down a long street at 1 meter per second for an hour. During this time, I count the number of trams that pass me by. Knowing that they follow a regular timetable in both directions, I'm initially surprised to note that only 15 overtake me, whereas 20 pass me head on. What's the average speed of the trams? So first off, there's lots of ways of doing this. So if you got the right answer in the end, then you probably did it a perfectly valid way. And always make sure you explain your working, because again, there'd be lots of credit even if you didn't get it right. But let's start with a diagram. So you have a person, and they're walking down the street at 1 meter per second. And so if we have sort of, these are head-on, this is the line of head-on trams, and this is the line of overtaking tram. Then if you imagine that this rectangle is a tram, they're traveling at speed v, and if they follow a regular timetable, we'll kind of use that to assume they have a constant speed. So we won't worry about them stopping at stops or anything like that. And so they have a regular timetable, so that also means that these trams must be separated by a constant distance d. So these are our head-on trams, and these are our overtaking trams. So this took me a while to get my head around, so I'll explain all of my steps. So if it's a bit slow for you, apologies. So I thought, okay, 15 overtake. So that's 1 every 4 minutes. And then 20 pass head on. So that's 1 every 3 minutes. And so using the trusty formula, speed equals distance over time. If we call the head-on trams 1 and the overtaking trams 2, then I'll scroll down. Then the speed of the head-on trams, v1, if you go from one tram passing the person to the next one, the distance that tram has travelled is d, the distance between the trams, but these are head-on, so the person has travelled 3 minutes towards the tram, so that's -3 times 60. In the time, 3 minutes. For tram 2, on the other hand, have I done this the right way around? Let's just think about this. We have the person going towards the tram, so they've travelled less distance. Yes. And they're head on, so there's 20. But we're not too worried about that. We've got 3 minutes. Okay, yes. So then for the overtaking trams, on the other hand, the distance they've travelled is a distance d plus 4 times 60, because the person's been walking for 4 minutes since the last one, in a time of 4 minutes. But these two trams are on a regular timetable, so they must be going at the same speed. So then, if we use the fact that v1 equals v2 and rearrange, then we're going to get an equation that will give us the distance d that they're travelling. So the speed of the first one is equal to the speed of the second one. So then we cancel these factors and we end up with 4d minus 3 times 4 times 60 is equal to 3d plus 3 times. If you take this 3d to the left and this term to the right, we'll end up with d is equal to 2 times 3 times 4 times 60. I quite like just keeping things sometimes in factors because then I don't end up with horribly big numbers, and they haven't asked us for the distance between the trams, so we don't need to give them a number or units yet for this. And now if I try and get a new page, insert page, blank page. Not quite what I was hoping for. Page break. Yay, okay. So now we have D, and we had an equation for V1 and V2, but we said they were the same, and we've been asked for the average speed of the trams, so we can just choose either of these to substitute in D. So let's choose V1. So that's equal to 2 times 3 times 4 times 60 minus 3 times 60 over 3 times 60. So then if we cancel 3 and 60 and 3 and 60 and 3 and 60, we end up with 2 times 4 minus 1, which is equal to 7 meters per second. So let's just double check we've answered the question. What's the average speed of the trams? Yes. So I'll just check the Q&A. Still a question for Nina. Is anything going on in the chat? Did that make sense to everyone?
So I think in the chats, a lot of people have been talking about the different methods that they've used. We've had people talking about using relative velocities as well, which is great to see that people are doing it different ways. But I don't think anything has come through for you to answer at the moment. Anna, I think you're
okay.
Good and
I'm
clear.
happy to, someone's just asked, can you provide the relative velocity approach as well, please? So I don't mind just quickly talking through that. It's a bit of a neat trick to do it a bit quicker. So I could.
Oh, if you're happy to,
great,
happy. Yeah. Lovely.
Okay. So there's a slightly different approach, which, as I just said, is a little bit quicker, but slightly less intuitive. So that is not the way my brain worked, but if your brain works this way, that's great. So instead, you can kind of look at it as sort of like waves. So if instead of you moving and working out the trams moving around you, if you take the person's frame, so they're stood still, then you have these head-on trams, just label them as head-on, and these are coming at you at a speed with v plus 1 because you're moving towards them, so you see them as coming towards you quicker. And then we have the overtaking, and these are coming at you with a speed v minus 1 because you're moving away from them. So then we have to think about waves, and with waves we have this equation: speed equals frequency times wavelength. Now these are kind of like waves because the trams are passing you regularly, they're equally spaced between them, so the wavelength here is our distance d. So you can kind of see the trams passing you as sort of like wave fronts, and this is almost like a Doppler effect. So we can write out our two equations. V plus 1 equals the frequency of the head-on collisions? No, hopefully not. The frequency of the head-on trams passing you is 20 times d, and the frequency of the overtaking trams is 15. So then we have two equations and two unknowns. So if we take the top equation and divide by the bottom equation, we have v plus 1 over v minus 1 equals 20 over 15. So then rearranging 15v plus 15 equals 20v minus 20. So then take 20 to the left and 15v to the right, we end up with 35 equals 5v. So again, v equals 7 meters per second. So if that was your kind of approach, then that is equally valid and really quite different. So yeah, physics can be done in lots of different ways. I'll just check the Q&A again.
Yeah, thank you so much for that, Anna. We do have 1 or 2 questions that have come through while you were doing that.
Mm-hmm.
So we've got somebody
yeah.
asking, oh, you can probably see them for yourself. You don't need
Yeah,
to read them out.
So the first one, this might sound silly, but why do you add or subtract D? So you don't necessarily need to, as I just showed with the second approach, but down here, when I added or subtracted D, I think you probably mean this bit. I was trying to calculate the distance that the head-on trams were traveling between each tram passing me. And then for the second, so then I ended up with the distance between the trams, but minus the distance I traveled. Whereas for the second one, for the overtaking trams, I ended up with the distance between the trams plus the distance I traveled. And then how do we know that the velocities of both oncoming and head-on trams are the same? So that's sort of a key point. You sort of have to have noticed that because these trams are on a regular timetable, you kind of have to assume or deduce that they must be going at the same speed in each direction. Otherwise, it kind of wouldn't make sense if you have a bus going from A to B and it goes from A to B much quicker than it goes from B to A, then it's going to have to wait at one end for a bit. So it's kind of an assumption you have to make that's not necessarily obvious. Yeah, hopefully that helps a little bit.
Yeah, thank you so much. And I think with the assumptions, Anna, I don't know, I look at this a bit differently to you because I'm not still solving problems the same way. But I think that's what makes these really interesting, is that there are these assumptions to make. And if you don't make them, your answer and solution is going to look really different, but still be valid.
Yeah, and that's where it's, again, really important just to write down all your thoughts, everything you've assumed, just everything, just in case that makes it make sense to the person who's marking.
And so lovely that these are not marked by a machine, so you'll get the benefits of an actual physicist or a material scientist looking through and seeing what your thought process was as well.
Yeah, exactly. Oh, and we've got more questions. Why can't we add the v+1 and v-1 equations? You can do whatever you want to, as long as you remove d. So you could, for example, rearrange this top one and have d equals v+1 over 20, and then substitute that into the second one. But you can't just add them both together, because otherwise you'd end up just with another equation in terms of 2 unknowns. So you just want to remove one of the unknowns. Also, do we assume that the trams start from rest when we start moving, or even if they start after some time, do we end up with the same answer? Yeah, so again, you kind of have to get into the question and get into the point where the trams are passing you regularly and not worry too much about when they started moving. So you're just in the situation where you're walking down the street and every so often a tram goes past you. You're not really worrying about when they're starting moving, or that kind of thing. Just assume they have infinite distance to travel and they just keep passing you.
Awesome. Thank you, Anna. Do you have one more question? Am I right in thinking
I do.
That? Lovely. We're ready when you are.
I'll just faff again. There we go. So, share screen. Question 6.
Give me a chance to switch my light on, so you're good to go. Yep, right. We can see your screen. You are
perfect.
all
Thank
set
you.
up.
So this last one, Hayley and Rob offer to paint the outside of a house. Hayley claims she can do the job in 2 days working continuously, and Rob says he'll complete the job in 3 days. If they're both hired to work together, how long should it take? So this is kind of a rate question. So if we think about per day, we have Hayley, and she says she can do the job in 2 days. So that means that she can do half per day. And then we have Rob, and he says he can do the job in 3 days. So that means he thinks he can do a third per day. So then we want them to work together. So the total rate, let's call it H plus bar. That would be a half plus a third per day, which would be 3/6 plus 2/6, which will be 5/6 per day. But then we want 1 whole one whole house to be painted. So to find out how long, we do 1 divided by the rate per day, and that gives us 6/5 of a day, or 1.2 days. So I went through that quite quick. Pop your questions in the Q&A if that didn't make sense, or if there are any bits that you got stuck on here.
That was a really fast one compared to some of the others.
Yeah. Yeah, question 5 was a bit nasty, I thought, but maybe it's how some people's brains work.
Yeah, I think often with these, the one that you find hard isn't always the same as the one that other.
Yeah. So we've got a question. Will there be any questions in the pat which have only worded answers, or is it all maths? Can't really remember. There might be ones. I don't know.
They're all numerical, so they're not explanation based.
Yeah, but then explaining is also
Yeah, exactly. Sort of part and parcel. You got to work through your maths to get it, but there aren't any essay based or explanation based questions. You know, answer to that. We've also had somebody who snuck a question into the chat, Anna. I just saw coming through. Oh, I saw that coming through. Where did it go? I think it was a division question, but I'm afraid it has disappeared. If you were the person who asked the question to the hosts and panelists, can you just quickly pop it in the Q&A for us, and then we'll answer that for you?
I think you can put stuff in the Q&A anonymously as well, if that helps. Oh, why do you do 1/5/6?
Perfect,
I
thank
do
you.
I do 1/5/6 because we're doing 5/6 of a house per day, and we want to do 1 house. So to find out how long it will take to do 1 house, we want to divide the total amount we want painting by how much we're painting each day. So then you can times both by 6, so you end up with 6/5. Hopefully that made sense. Oh, perfect. Thanks, Annabelle. For the last question, could you use the product sum as a quick trick, or is this just a fluke? By the product sum, I guess you mean that we have 3s and 2s and 5s and 6s. But I'd probably always just write out your fractions like I did. So I went from a 1/2 and a 1/3, but I wanted in 6 because that's the lowest common denominator, and so I wrote them both over 6 before I added them together. So I guess just be careful that you don't make any assumptions that might not be true.
Awesome, thank you so much, Anna. That was lovely to have your 3 questions. I wonder if Nina is ready to return to her very tricky question 1. We can have a quick chat about that, and then I should have about 10 minutes to do a general Q&A about the PAT session. So I know a few of you do have questions, and I can see those coming in, but don't worry, we're going to talk about those now. Nina, how are you doing?
Oh, hi, hello. Just had quick dinner.
Perfect, that's why we were giving you a break, Nina. How are you feeling? Are you ready to have a look at question 1 for us again?
Yes, yeah.
Amazing.
I realized what the problem was.
Perfect.
Yeah, so let me just go through it slowly and explain what I was trying to explain. Does that work? Yes, it works. Okay, so the equation we got in the end was that, so we wanted our small h to be less or equal to 0.25. And we saw that when you consider potential and kinetic energy, an expression for the small h would be 0.75, so 3/4 to the power n. So this should be less or equal to 0.25. Yeah, so you take log on both sides. This is fine. You can take the power out of the log. And then, yeah, the point I was trying to make for the log function itself, as I said, if this is your argument, if this is log x, it is negative for arguments smaller than 1. So these two numbers are negative. Yeah, I explained it kind of backwards, just how my brain works. But yeah, so these two numbers are negative, which means when you want to divide by this log 0.75, n would become larger or equal to log 0.25 over log 0.75. And then this gives you then n is larger or equal to whatever the number was, 4.8 something. So yeah, the guys who were saying that you, like when you divide, you change the sign because of the sign of the log function. Yes, you're right. So I hope this is clear, makes sense.
Perfect. Thank you so much, Nina. That was really helpful. And I love that, probably not deliberately, but you're reinforcing this idea of making sure we draw diagrams as every stage. So that is lovely. Thank you so much.
Okay, good. I'm glad we
Now, I can see that we're starting to get people going, okay, we've done some problem solving. So I'm going to open up the Q&A now to some general PAT questions. So I'm going to start dealing with these. We've got kind of just over 5 minutes, and I hope that you find our introduction helpful. So just in the order they're coming through to me, can see people asking about the tech that people are that Nina and Anna are using, and whether this is helpful for online interviews. Online interviews, just to bring everyone into the loop, are a little bit further down the line than where we are now. So we are thinking about preparing for the PAT, which we will sit in October. If you are then shortlisted for interview, or indeed, if you take a physics interview at any other university, you may be interviewed online. In which case, being able to write online can be very helpful. I know from Oxford's point of view that every tutor has a different preference for how they interview. Some people will want you to share an online whiteboard like Nina and Anna have done. Some tutors will recommend that you have a tablet available to you and will make sure that that can happen. Other tutors are happy with you showing a piece of paper. So I would say very much is a combination of what the tutor likes, but also making sure that you are able to do your best. Okay, I hope that one helps. Moving through, we've got topics on the PAT syllabus, and this has come up a few times, both in the chat and in the Q&A. So your guide to what you have to learn for the PAT is nothing to do with checking your exam syllabus. It's check the PAT syllabus first. So I've shared these links. For those of you who have just joined this week, you'll get an email tomorrow morning. It will contain a link to the recording of this session and some helpful links, including the link to the PAT syllabus. That is what you have to go and learn. So if there is something in the PAT syllabus which you have not covered, you will have to go and learn it. And for that, that's when all the resources come into play. So we'd recommend, first of all, having a look at some of the other A-level exam boards, or if you're not studying for A-levels at all, have a look at those A-level exam boards revision guides. They should cover a lot of it. And then if there's anything you're still unsure of, you can start branching out. So the Scottish Advanced Higher exam guides are really useful for covering exactly the same level. You could look at some of the IB exam guides, and there are some other resources out there as well. But you will need to check the PAT syllabus rather than relying on your own exam syllabus, which I hope helps. Let's see if there are any particular themes. So yes, it is confirmed that Oxford Physics interviews will be online this year. So that is a nice quick answer that I can give now. And then how should we mark past PAT papers with more than one mark? How are marks for working distributed? So correct me if I'm wrong, feel free to pop something in if I've got this wrong, but I think what you're asking is how important is the final answer versus how important is the process of guessing your answer. So what I'd say there is that it all comes down to how it's marked, which is lovely. So I said at the start, PAT is a required admissions test for physics, physics and philosophy, engineering and materials science. If you are applying for physics at Oxford and you take the PAT, your PAT test will be marked by physics tutors. If you are applying for engineering science at Oxford and you take the PAT, your PAT will be marked by engineering scientists. And that means that they are able to really thoroughly look at all of your answers. And they're able to look for what you were trying to do. So that's why when we're talking about things like what assumptions did you make, we're saying, well, write it down, make sure you've made it really clear. When we're saying, hey, it doesn't matter what method you take, this is why. It's because your paper will be marked on its own merits. So it's not a simple 1 mark for this, 1 mark for this. It's an overall mark. It's in a way a bit harder to give you a definite answer for when you want me to just say, I can tell you it's 1 mark for this, 1 mark for this. It's a little bit more complex than that, but it means that you get a lot of credit. And really, we're trying to give you credit for everything that you show rather than penalizing you for something that you don't show. And so that would apply for physics papers being marked by physicists, engineering papers being marked by engineers, materials scientists marking materials science. I think that covers those kind of questions. Okay, so I've had a few questions about test centres. Your school will have to register as a test centre. This system went live today. So some of you might be aware that we're using a different company to administer our tests this year. Honestly, that makes no difference to you whatsoever. All it means is that until today, your school wasn't able to register as a test centre. As far as I know, there is no reason why any school would not be able to register as a test centre, and international schools can register as test centres as well. So there may be some differences in how the test is administered. I know in some countries it will be a fully paper test rather than the hybrid format. In the UK, it will be the hybrid format. So I can't answer that specifically for every country, just because I don't have that list. But registering as a test centre is pretty simple, and it shouldn't be any different to your school registering for you to take any other exam. The great news is, though, it's only June. Your school has to be registered at some point before September. We've got loads of time to deal with this. If your school are really having trouble, put them in touch with us. We will figure it out. You also don't need to sit your test at your own school. So if your school doesn't register as a test centre, but the school a couple of miles away does, you could register to sit your test there. So lots of things there that we can deal with. So don't worry too much about that one. So I hope that answers that one. And a few. Okay, so then we've got a few questions about equation. I'm going to do this in a one. I'm trying to group them. So I'm going to do equation sheets, calculators, and modeling numbers. And I think that should cover a few of these. If I don't get to you today, please do not worry. We've got lots more time. So in order, there are no formula sheets for the PAT test. If you're going to use an equation, you need to know it. It is tricky, but this will also be the case in so many university exams that it's really good practice and it's going to help build your fluency. You've got months to prepare. The test isn't until October. So just as you're starting to do your revision, as you're starting to practice, try to get into the habit of using all of these tests. In terms of modelling things like gravity, Usually in the questions in the PAT, you are given the constant that you are being asked to use. So say you're asked to use H, you will be told it's 6.2. Okay, so you're told to use G, be told it's to be used as 10. If you are not told what to model it as, so if you're not given a value for G, start with the sentence, taking G as, and write down whichever you decide to use. Okay, so when you make assumptions, just share them with the examiner, and then you're home and dry. So you should be given them. If you're not, write down what you decide. What's the last? Calculators. Calculators, you will not be allowed to take a calculator into the PAT this year. Instead, because we are using this hybrid format, there will be a calculator available as part of the online test. This is great because it means everyone is using exactly the same calculator, and we do not have the headache of trying to narrow down from an entire world of calculator serial numbers the ones that we are happy for you to use. The questions in the PAT are not calculator heavy. The PAT for a long time was completely non-calculator. So in the last few years, we've allowed calculators at all. I would say this is not something to be concerned about. There will be an example. As I said right at the start, there will be a mock-up of the test format available. You can have a go and have a look at it. You are simply not going to need to do anything so complicated on a calculator that having a different calculator is going to confuse you. So you will be absolutely fine. I am not going to talk about choosing Oxford colleges today, simply because we're running out of time. I'll try and cover that at some point over the next few weeks. So in every single session, I'm going to try to do the same introduction, talking about what PAT is, where we are, any key dates, and I'll try to do a Q&A at the end and get to some different questions every week. The open days for Oxford are tomorrow, and I've seen a few of you saying you're coming to visit us. Great, have fun. The physics department will be open. There'll be a chance to tour the undergraduate teaching laboratories. You could visit a library as well. There'll be a chance to go to colleges. There'll be a chance to talk to some undergrads, recent graduates like Nina and Anna, a chance to talk to some tutors, a chance to talk to people like me, people like Sean, who was on the call earlier. So no particular tips, have fun. Last one I'm going to answer is a few people asking, what's the test? What's the mark? What's the mark? What do I need? The answer is it's never a simple cutoff. Your PAT forms part of your application. The tutors will use it as part of their decision as whether or not to shortlist you. There are admissions reports that you can read if you are feeling particularly interested in the statistics of physics admissions in Oxford, but you do not have to. There is a huge variation in scores every single year. I think last year it went from about 4% to 97%. And there is not a hard and fast cutoff. Your personal application will be taken into consideration. So I hope that answers a few of those questions. Please don't worry if I don't get to all of them today. Like I say, we've got a few more weeks and I'll send your email out tomorrow. For now, we have come to the end of our second webinar, and I will see you all in another week. So next week, we will be having another study session with a teacher called Justin, who will take you through another set of problem-solving activities, similar to the ones that Rachel did last week. I'll share the recording tomorrow. I hope everyone has a lovely week. Thank you so much. Goodbye, everyone.